In this video, we'll continue our study of logarithms by examining the properties of logs. You may have seen these properties before, including how to simplify logs that are added or subtracted. We'll investigate these properties and much more. Precalculus Online starts right now. Let's take a look at 5.5, Properties of Logarithms. Now, I feel like a lot of these properties are familiar, but maybe extended, and the example is a little bit more difficult than what you may have seen in college algebra. So let's go ahead and take a look at some of these properties. For this properties section right here, we're going to assume that the A is positive, that the M is positive, the N is positive when we get to it, and that R is real. So it could be positive, negative, or zero. So here are some of the properties of logarithms. Number one, log base A of 1 is equal to 0. Number two, log base A of A is equal to 1. Number three, log base A of A to the R power is equal to R. And number four, A raised to the power that is log base A of M is equal to M. Number five, log base A of M plus log base A of N is equal to log base A of M times N. So this particular log property says the following. If you take two log statements that are in the same base and you add them together, you can simplify that to a single log by multiplying the two arguments, M times N. Now in the same vein, we also have log base A of M minus log base A of N. You do what's natural here, you divide. So it becomes log base A of M divided by N. Next, we have log base A of M raised to the N power. That is equal to R times log base A of M. And what a lot of people view this one as is if you have a power on the argument, it can come in front of the log and multiply. So that's what you'll hear some people talk about. And then lastly, this one is sort of a neat one here. A raised to the R power. So A is positive, but R is any real number. That can be rewritten as E raised to the R times natural log of A power. And sometimes you'll need this kind of rewriting when you get to calculus to do some things. All right, so that's what the basic log properties are. Let's prove a couple of these using some formal statements. And there's a proof on your homework as well. So let's go over the proof. This first proof, I want to prove this last one on the first column. So we want to prove that A raised to the log base A of M, that whole thing is equal to M. Now first let's talk about what this statement says and see that it makes sense. Remember that we learned that a log base A of M, that's equal to some number, I'll call it x. And what that represents is the exponent. In particular, it's the exponent that you need to raise A to in order to get M. So this statement on the left says, if I take A and I raise it to the exponent that, if I raise A to this number, I get M, the result then becomes M. It's sort of like destiny. The log in base a of m is the number that you raise a to in order to get m. So when you actually raise a to the log base a of m power, you get m. That's exactly what you're supposed to get. So let's prove this and see where the proof of this statement comes from. So first let's set up some stuff here. So let's let a function f of x be equal to a to the x power. So I've created a function. Next, I can define what the inverse function is, and we know this from previous lessons. Then f inverse of x is equal to log base a of x. So since f was the exponential function, the inverse must be the log function. And since f and f inverse are inverses, we know that f of f inverse of x must be equal to x. That was the verify that f and f inverse are inverses statement from a few sections ago. And this must be true for all x in the domain of f inverse. But what does that really say? Well, it really says, let's suppose I use an m now. So m is a definite number here. It says that f of f inverse of m must be equal to m. All right, that's good. But what else do we have? Well, we can take f of f inverse of m. F inverse of m comes from 3 lines up. It's log base a of m. And now I can take log base a of m and evaluate that inside f. But f was the exponential. And so f of log base a of m is really a raised to the log base a of m. But that's equal to m. So there you go. That's the proof. Let's go ahead and prove the sum formula for logs. So prove log base a of m plus log base a of n is equal to log base a of m times n. So let's prove that. So again, when you do a little proof, you have to do some setup. So let me go ahead and declare that x is going to be equal to log base a of m, and y is equal to log base a of n. If I convert both of these back into exponential form, I get a to the x is equal to m, and a to the y is equal to n. Now when you do a proof and you're trying to prove an equality, you can start on either side of the equality and do some work to get to the other side. In this proof, I choose to start on the right side. So I'm going to start with log base a of m times n. My goal is now to get the left side, where it's log base a of m plus log base a of n. Well, what is log base a of m times n? That would be log base a, and m is equal to a to the x times n, but n is equal to a to the y power. And then you start thinking about how you can simplify some of these things. Well, I can simplify this by doing the following. I can say log base a of, and then we have we have a to the x times a to the y. That becomes a to the x plus y. But what is that equal to? That is equal to x plus y. There are several reasons why that is the case. You could turn it back into its exponential and solve it. You can say, since the log is the exponent, that you would raise a2 to get a to the x plus y. What exponent must that be? Well, if you're getting a to the x plus y, it must be x plus y. So several reasons that you can get that. Well, what was x? X was this log base a of m plus, and what was y? Log base a of n, and that's exactly what we were looking for. So we have proved that log base a of m times n is equal to log base a of m plus log base a of n. Let's look at example number 1. Write as a single logarithm 3 times log base b of x minus 4 times log base b of y minus 1/2 log base b of z. The first thing that we need to do is move the coefficients into the log as powers. So the 3 goes in as a power of the x. The 4 goes and becomes a power of the y. And 1/2 goes and becomes the power on the z. But we know that 1/2 as a power is the same thing as the square root of the number. So we go ahead and write this as the square root of z. Now I have a rule, and it's based on the rules that you saw on the first page. But the rule is very simple. If the coefficient in front of a log is positive, then that argument goes on top. If the coefficient in front of a log is negative, then that argument goes in the denominator, in the bottom. And that's how I simplify these logs. So let's take a look here. So first one, log base b of x cubed. Is the coefficient in front positive or negative? It's positive. So that means this one is going to go up top. So it's going to be log base b of x cubed. Next, look at the sign of the coefficient of the next term. Positive or negative? It is negative. That means y to the 4th goes in the denominator, goes on the bottom. Next term, negative log base b of the square root of z, it's negative, so it goes on the bottom. This will save you from having to determine if it was a double negative, 2 negatives in a row, and you get these compound fractions with a number divided by another number, all of that sort of stuff that's hard to simplify. This one saves you the trouble of all of that. So this is the result right here. Notice that you only write the log statement one time. It's not a different log statement for the numerator and denominator. It's a single log of, and then you write in all this other stuff. Let's look at example 2. Write as the sum or difference of logarithms express powers as factors. So in this case, we're not creating a single log. We have a single log. We're breaking it apart. So you can use my rule in reverse. So everything is going to be log base 6. And then what is the first factor on the top? It is x to the 4th. Plus, we have another factor on the top, so it's plus log base 6 of the square root of x squared plus 1. Next, we have a factor from the bottom, so it's subtract because it came from the bottom. Log base 6 of x minus 5 cubed. Next, we take the powers and we move them to the front. So we're going to have 4 times log base 6 of x plus The square root turns into a 1/2 exponent. That exponent then comes to the front. So it's 1/2 log base 6 of parentheses x squared plus 1. Notice we have to use parentheses here because if we didn't, it would look like it's log base 6 of x squared, and then after the fact, it's plus 1. It's not. It's log base 6 of the expression x squared plus 1. Same thing on this last statement. The 3 comes to the front, log base 6 of x minus 5. And then the question is, can you split up the x squared plus 1? And the answer is no. You have to leave it in the parentheses. You cannot split that up. And that's the answer. Let's look at example number 3. Let p equal log base b of 2 and q equal log base b of 3. Simplify each of the following using properties of logs, writing your answer in terms of p and q. So I'm working with 2's and 3's in this case. So in question A, log base b of 18, how can I express 18 with 2's and 3's and then powers of 2's and 3's? Nothing else. Well, the answer is this becomes log base b of 2 times 3 squared. Then, using properties of logs, I can split this up. It becomes log base b of 2. Since it was times in the middle, it's plus on the outside here. Log base b of 3 squared. Next, I can move the power on the 3 to the front of that logarithm. So it's log base b of 2 plus 2 times log base b of 3. And finally, I make my substitution. Log base b of 2 is equal to p, and log base b of 3 is equal to q. So the answer is p plus 2q. Let's look at part B, log base b of 8 over 9. So this would be, in terms of 2's and 3's, log base b of 2 cubed over 3 squared. Since we're dividing inside a log, we can split that up by using subtraction. So we get log base b of 2 cubed minus log base b of 3 squared. The powers on each of these come to the front. So we get 3 times log base b of 2 minus 2 times log base b of 3. And we make our substitutions again, the p and the q. So this is 3p minus 2q. In example 4, express y as a function of x. C is a positive constant. So we have natural log of y is equal to natural log of x plus the natural log of c. So the first thing that we can do, there's a couple of ways that you can do this, but the first thing we can do is we can raise each side as a power of e. So I get e to the natural log of y is equal to e to the natural log of x plus the natural log of c. Leaving the left side alone for a second, e raised to the natural log of y. I can simplify the exponent here, and that gives me e raised to the natural log of, and be x times c. When you do these problems later on, it's customary to put the c in front. So I'll just write natural log of c times x. Then, using the rule from before, which is a raised to the log in base a of m is equal to m, We recognize these as a version of that, except we have e, and then the log in base e is actually natural log. So e raised to the natural log of m is equal to m. That tells me that each of these simplify to just what the argument in the logs are, and we get y is equal to cx. And that's the answer. Because we're looking for a function of x with y equals that function. All right, let's connect with biology. The population of an ant colony can be modeled by P of t is equal to 120 times e to the 0.2t, where t is the number of days since development. How many ants will there be after 20 days? Well, 20 days, that's a t value. So I'm going to plug that in for t, and how many ants, that's a p value. So I want p of 20, and you plug this into the calculator and you get 6,551.78. So we'll round that to the nearest whole number. And then question B, after how many days will the population reach 2,000? So the population 2,000, that's a P. After how many days, that's a T. So we're solving for T. So we want the model to be equal to 2,000. So 120 e to the 0.2t is equal to 2,000. Divide by 120. So e to the 0.2t is equal to 2,000 over 120. I would just go ahead and write out all the numbers. Don't do anything in the calculator yet. Save that for later. Now, another way that we can solve this is by taking the natural log on both sides. So the natural log of e to the 0.2t is equal to the natural log of 2,000 over 120. The question is, what happens when you take the natural log of e to something? Well, again, that's one of our properties. Log base a of a raised to the r power is equal to r itself. So this statement, rewritten in terms of base e, says that the natural log of e to the r is equal to r. They are inverse functions and they undo each other. So the left side here, natural log of e to the 0.2t is just 0.2t. And that's equal to the natural log of 2,000 divided by 120. And then divide by the 0.2. On application problems, we want to get decimals. And let's try 2 decimal places and see if it gives us enough decimals to work with. So plugging that into your calculator, you get 14.07. Please write the unit, and the unit is days.